Okay, so today we're talking about 2.1, the basic set concepts. We have a few objectives today. We're going to use three methods to represent sets: the word method, the roster method, and the set builder notation. We're going to define and recognize the empty set. This is like the zero in arithmetic. We're going to use the symbols epsilon and not epsilon to represent members of a set and not members of a set. We're going to apply set notation to the sets of natural numbers, which would be our first infinite set. We're going to determine a set's cardinal number, the number of elements in a set. We're going to recognize equivalent sets, sets that have the same cardinal number. And we're going to distinguish between finite sets, like the alphabet, and infinite sets, like the natural numbers. Then we're going to recognize equal sets, sets that not only have the same cardinal number, but have exactly the same elements in them. So now what we want to do is we want to define the set. A set is a collection of objects whose contents can be clearly determined. And so the idea is that the set must be well defined, right? And that's why that's highlighted. So maybe we're talking about the set of basketball players. Right? And so now I go, well, you played basketball last week, so you're a basketball player. And somebody else says, well, you've never played on a high school basketball team, so you're not a basketball player. So this is a collection of objects which is not clearly determined, basketball players, okay, because it's not well defined. So to be clearly determined, there has to be no dispute among the members of the set, okay? And so the members are not going to be in dispute. The math word for that is elements, right? So we're going to have a well-defined set so that there is no dispute among the elements or members that belong in a set, all right? So now what would be a well-defined set? Well, a well-defined set would be NBA players, right? You either play in the NBA or you do not play in the NBA. Okay, there's no dispute among that. All right, now I may not know all of the players who play in the NBA, but I can actually Google it. I can look it up on, NBA.com or something, I'm sure, right? And so the last thing is the order in which the elements of the set are listed is not important. A lot of times the way we list the elements of the set are just alphabetical order or something like that, right? So I may put Kobe Bryant in the set before LeBron James, and that's not to say that Kobe is better than LeBron or LeBron is better than Kobe. It's just that those are members of the set, and those are not in dispute because they are definitely NBA players, right? So we do have a couple of different methods for representing sets. Capital letters are generally used to name sets. And so this will be true through the course. So this is going to be true for us. Okay? I'm only going to use capital letters for sets. Now, a word description is describing the members sort of in a sentence. Okay, so set W, see the capital letter, is the set of the first 5 presidents of the United States. So this is a clearly defined set. We know who all the presidents of the United States are. We know which the first 5 presidents are. So this would be a sentence form and a word description of this set. The roster method is just a listing of the members out. Okay, so instead of a description, we're actually going to say W is. And then these are called braces right here, okay? Braces. Washington is the first one, Adams, Jefferson, Madison, Monroe. Now these are in chronological order, but that's not to say that Washington was better than Adams or that Adams was better than Jefferson. We just had to put them in some order, and so we put them in chronological order, okay? Commas are used to separate the elements of the list, each of the individual presidents, and the braces are used to designate that the enclosed elements form a set, all right, as well as the capital letter right here. Okay, so those are two of our three methods for representing a set: word description and roster method. In example 1, we want to represent a set using a description. So our first one is we want to write a word description of the set P equals A, B, C, D, E, F, right? So what is the solution here? Pause for a moment and think. Write it in your notebook. Okay. But the word description would be the set P is the first 6 letters of the alphabet. Okay, so those are going to be the first 6 letters of the alphabet. So that's a word description of this set right here, P. And the elements are, you got to define the set P. There's the capital letter, okay? There's the set P is the capital letter, is the first 6 letters. Those are the elements of our well-defined set of the alphabet, okay? So now, example number 2. We want to represent a set using the roster method. So using the roster method, set C, okay, there's our capital letter again, is the set of U.S. coins with a value of less than $1. Express this set using the roster method, right? Well, they've already told us that we're supposed to call the set C. So here's my set C is equal to, and here's my braces to denote the beginning of the set. And the order that I'm going to choose to put them in is ascending value of value. Okay, ascending value. So we're going to use penny, smallest value, nickel, next smallest value, dime, quarter, and $half. Because it does say of less than $1, and the $half is an actual coin, but we can't include the Susan B. Anthony because it is actually exactly $1. So we have 5 elements here of coins with value of less than $1. So this is the word description right here, and then this is the roster method of that same set. Okay? So those are the first 2 types of methods that we have for representing a set. Now we want to use a slightly more mathematical idea, right? We're going to use this idea of set builder notation. Okay, it's very formal, but it allows us to kind of bridge the gap between the roster method and the word method in mathematics. So here W, notice again the capital letter is equal to this. The brace denotes the beginning of the set, X. Okay, so X is going to be all of the elements in W. So this is a variable. It is going to vary to become each member of the set. This bar gets read as such that, okay, and here's our brief word description. X is a day of the week, or X is a letter of the alphabet, or X is an NBA player. Those would all be word descriptions inside our set builder notation that would allow us to describe the set that we are using. Okay, so before the vertical line is the variable, and after the vertical line is the condition. So that's very important. All right, so before the vertical line is the variable, that represents the elements, and then after the vertical line is the condition. Okay. So here we have another example. All right, converting from set builder notation to roster, express the set. So here it is in set builder notation, right? This guy right here. And it says X is a month that begins with the letter J. Okay, so in a roster method, remember, again, I need my A. So there's my month set. Here's the start of my set, letter J. I'm just going to go in chronological order, right? January is the first month of the letter J, and you have February, March, April, May, June is the next month that starts with a J. July is the next month that starts with a J. And then if you go August, September, October, November, December, you realize that it's just those three. And so I close it up. And so this is the roster method, all right, representation of the set builder notation up above. And that makes us happy. Okay? So now we want to talk about the empty set. The empty set is a very important idea because it gives us a zero with which to deal. Okay? And the empty set, also called the null set, don't forget this one, the null set, is the set that contains no elements. Okay? So it really means there's nothing inside there. Nothing inside the set. Alright? The empty set is represented by the braces with nothing inside. That's where I'm getting this definition from. Or it basically took the zero, the big O, and put a line all the way through it, right? So this is kind of a very fancy set zero in that uppercase notation. These are examples of the empty set. X, where X is a month that begins with the letter W. Well, there are no months that begin with the letter W, so this would be an empty set. For right now, the word description, the set of all female presidents of the United States, is also an empty set. We've never had a female president before, and so this is an empty set, okay? At least in, for the near future. Example 4, recognizing the empty set. So I want you to really make sure that you can do this, right? Which of the following is the empty set? So we're just going to put in a yes or a no. Well, this is a set, but look, there's something inside. There's a zero inside. So this is going to be a no. This is not an empty set, okay? It contains one element, one member, the number 0, okay? Nothing. Well, nothing is not an empty set either, okay? And the reason why that is because it is not in a word description. This is basically just a word, okay? Nothing is just a word. It doesn't say the set A that has nothing in it, okay, or the empty set which has nothing in it. It just says nothing. So that makes me sad. All right, so here's what about X? Such that X is a number less than 3 or greater than 5. If I started to do this out in a roster method, right, numbers that are less than 3 are numbers like 2 or 1 or 0, right? Numbers that are greater than 5 are 6, 7, 8, 9, right? So all of these things are in here, so this certainly is not going to be an empty set. So this is going to be a no also. What about X such that X is a number less than 3 and greater than 5? Okay? Oops, let me erase that. Okay? Or greater than 5. So what we want to do is, so if X is a number less than 3 and greater than 5, well, there isn't a number less than 3. We're looking at, again, numbers like 2, 1, and 0, and greater than 5, right? 6 is not less than 3, 7 is not less than 3, and so this is going to be an empty set. So this one right here is the only one that gets the yes, because it has no values in it, just like the set of all female presidents of the United States is not in the set. So now we have notation for set membership, right? So here's the epsilon that I was talking about. So the fancy script E is epsilon, and then the fancy script E with the line through it is the not an element of the set, right? So we use the symbol epsilon, is used to indicate that an element is an object, is an element of a set. The symbol, epsilon, is used to replace the words is an element of, right? So that's the shorthand for the epsilon. And so the symbol not epsilon is used to indicate that an object is not an element of a set. And the symbol epsilon is used to replace the words is not an element of. So this belongs and this does not belong. So we want to use them, okay? So determine whether each statement is true or false, right? Is 5 an element of the set? 1, 2, 3, 4, 5. Well, of course, yes. This one is definitely true because there's the 5. It's definitely an element of the set. Now, what about Z is not an element of A, B, C, D, E, F? And of course, this is also going to be true, right? The set does not continue on. So this is not the full alphabet. This is just the first 6 letters of the alphabet. Right? So Monday is in the set X such that X is a day of the month. Oh, well, wait. No, this isn't true. This is false, right? Because, let me draw a nice F here. This is false because Monday is a day of the week, not a month. All right? And then Obama is not in the set X such that X is a POTUS. Well, POTUS is short for President of the United States. Well, President Obama is a President of the United States, so he is a member of the set, so not being a member would be false. So this is also going to be false, okay? So Obama is a member of the set Presidents of the United States, and Monday is not a day of the month. Alright, so now I have made those both true. Okay. So now we want to talk about our first infinite set, the set of natural numbers. So n is typically what we use for the set of natural numbers. Okay, you don't see it in many other places, the capital N. And then we have the 3 dots, which is called ellipses. Okay, so the 3 dots right here is our ellipsis. After the 5 indicate that there is no final element, and that the list goes on forever. This is because the set of natural numbers is an infinite set. Okay, it's an infinite set. Just goes on and on and on forever. So that's important to note. All right? So example 6, representing sets of natural numbers. Excuse me. Express each of the following sets using the roster method. Set A is the set of natural numbers greater than 5. Well, if I'm going to use the roster method, right, I need to define my set A is equal to, and start the set off, greater than 5. Well, 6 is greater than 5. 7 is greater than 5, 8 is greater than 5. In fact, there's an infinite number of values that are greater than 5. So now I'm going to use my 3 ellipses and close my set off so that I know that this is going to continue on and on and on forever. Okay? Now, this is a word description, and I put it in the roster method. This is a set builder notation, and I want to put it in the roster method. So E is the set, well, X is a natural number and X is even. So you need all the even natural numbers. So 2 is an even natural number. 4 is an even natural number. 6 is an even natural number. And then there's my ellipsis, my 3 dots. I'm going to close up the set. The general rule of thumb for this is use enough elements so the pattern is established. Okay? So here, 6, 7, 8, dot, dot, dot. This just sort of indicates that I'm going to go up by 1 each time. 2, 4, 6. This indicates I'm going to go up by 2 each time. if I was going to do exponents, I probably would have had 2, 4, 9, 25, and then maybe my 3 dots, okay? But you just need enough elements so that the pattern is established, so that when you put in the ellipsis, that the person knows what is actually following afterwards, okay? Now, the next 2 slides I want to go over just real briefly, inequality notation in the sets. Pause, take a look at how this inequality gets written in the set builder notation and the roster method. The equal to, right, is a little bit different, and so it adds an element. Here's your greater than, okay, and your greater than equal to. As soon as you take a look at the picture, you'll understand what the idea is there, all right? And basically, it's just the difference between greater than 4 doesn't include the 4, greater than equal to 4 does include the 4, all right? Now, this is our compound inequality, so the x is going to be in between, and so certainly only 5, 6, and 7 are in between 4 and 8. But when you do the greater than equal to, you also need the 4 and the 8 on the end. So this is the difference between the include and the not include in our inequality. So take a second, pause the video, and take a look at this chart, and then continue on when you're comfortable. All right. Cardinality and equivalent sets. Now please be very careful. We use equivalent sets to mean something very specific in this section, okay? So definitions are just so important, so pay attention to them. The definition of a set's cardinal number, the cardinal number of a set A, represented by n of A, is the number of distinct elements in set A. The symbol n of A is read, just like I've been reading it, n of A, okay? And hopefully this makes sense, because n is the number of elements in the set. Okay, so n just basically stands for number. Note, repeating elements in a set neither adds new elements to the set nor changes its cardinality. Okay, so repeats are not counted twice. Not counted twice. And this is very important for determining cardinality and equivalent sets. Right? So now let's look at a couple of examples. Example number 8. Please find the cardinal number of each of the following sets. Okay? So the cardinal number here is n of A, would be the correct way of writing this, is going to be equal to, well, there's 1 element, 2 elements, 3 elements, 4 elements that are not repeated. So it's 4. Okay. Here, n of B is going to be equal to, hopefully you didn't say 0 or none, or that it was the empty set, because there is 1 element there, the 0. So the cardinality of that set is 1, which is why it is not the empty set. Remember this, the fancy 0 stands for the empty set. And then C is 13, 14, 15. Well, here are our ellipses again, right? So 16 is here, 17 is here. They just didn't want to write them all. And then we're going to stop at 23, right? So the n of C is going to be equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So if we write them all out, excuse me, if we write them all out, we're going to get 11, okay? And that makes us happy. So what is the definition of equivalent sets then? Well, at the beginning I told you that the definition of an equivalent set would be set A is equivalent to set B, means that set A and set B contain the same number of elements. So for equivalent sets, the cardinal numbers are equal. okay? The cardinal number is the same. That's the big idea here, okay? That's what you want to take away from this. So basically, the same number of members, okay? That's what an equivalent set is. Equivalent set, right? I have 4 drawers and I have 4 socks, so those are the same. I can put 1 sock in each drawer. I have 6 dogs and I have 6 dog collars. Those sets are the same because I can put 1 collar with each dog. So the same number of members. And that's why we call them equivalent sets, right? Because there's a one-to-one pairing. These are equivalent sets, okay? So X is a vowel, A, E, I, O, U. That's 1, 2, 3, 4, 5 different elements right there. And B is a natural number greater than or equal to 3 and less than or equal to 7, which also has 1, 2, 3, 4, 5 elements. So the cardinal number is exactly the same. The cardinal number is the same. And so because they can be paired with exactly 1 element, these are equivalent sets. So dog with dog collar, cat with cat food, sock with sock drawer, vowel with number, right? How about a musical note and its frequency, right? That would be an equivalent set. 2 different ways of representing the same idea. So what I've been saying all along is summed up in this slide. There is a one-to-one correspondence in equivalent sets. If set A and set B can be placed in one-to-one correspondence, then A is equivalent to B. If set A and set B cannot be placed in one-to-one correspondence, then A is not equivalent to B. All right? So let's take a look at an example. We want to determine if the sets are equivalent. So here's our list, our word description, the set of 5 countries shown. So, right, kind of a word description. B is going to be the set of the average number of years women in each of these countries prefer men who are older than themselves. All right, so the average number of years the women in each country prefer men to be older than them. All right, so it's kind of an interesting chart here. But you'll notice, right, that 3.3 and 3.3 are repeated, and also 2.8 and 2.8 are repeated. So we do want to be careful because these repeated values are not going to show up twice in our set. All right. So method 1, try setting up a one-to-one correspondence. So here's the picture. And of course, Zambia is going to go to 4.2. Colombia is going to go to 4.5. Poland and Italy go to 3.3. And the U.S. goes to 2.5. So because I cannot set up a one-to-one correspondence, the answer to the question, determine if the sets are equivalent, is no. The sets are not equivalent. Okay, so the sets are not equivalent. N of A is equal to 5. N of B is equal to only 4. And so those sets are not equivalent. Not equal to each other. All right. So finite sets and infinite sets. So we've already been talking mostly about finite sets, right? NBA players. presidents of the United States. And we've talked about infinite sets. The natural numbers are an infinite set. Okay? Finite sets and infinite sets. Set A is a finite set if n of A is equal to 0, that is, A is the empty set, or n of A is a natural number. A set whose cardinality is not 0 or a natural number is called an infinite set. Okay, so the finite set is going to be a set whose cardinality is not 0 or a natural number is called an infinite set. This might be a little bit confusing. If you read the book, it might be a little bit confusing. But hopefully you all realize that a finite set has a bound on it, okay? That there is some upper limit, okay? So even if the upper limit is a trillion, right, or our national debt is 16 trillion, there's an upper limit on that. Infinite, by definition, right, if we look in Webster's, has no bound on it. I keep counting and counting and counting, and I get to 16 trillion, and there's a 17 trillion. And I get to 100 trillion, and there's a quadrillion, right? So you can always have one more element. That's what the no bound means there. So an infinite set has no bound. You can always have one more. A finite set has a boundary on it, right? It has some sort of a limit where you've got to stop and you can't put any more in it. All right? Now we have equal sets. Now equivalent sets where cardinal numbers are the same. The equal set has the distinction of exactly the same elements, okay? So regardless of the order or possible repetition, we symbolize the equality of sets A and B using the statement set A is equal to set B. All right? So just a little recap. Equal means same elements, while equivalent sorry about the spelling, means same number of elements. Okay? So, if you are going to talk about the alphabet forwards and backwards, those are going to be equal sets. They have exactly the same elements. It's just that A is at the beginning at one and at the end of the other. Equivalent sets means I have 6 different dogs, I have 6 different dog collars, I can create a one-to-one correspondence. They have the same number of elements. But the dogs and the dog collar set are not the same. A dog collar is not the same as a dog. So they are not equal sets, just equivalent. Okay? And so that brings us to our very last example for this one. We want to determine whether the sets are equal. If you look, the 4 is here and here, the 8 is here and here, and the 9 is here and here. And so these are equal sets. You've got 1 and 1, 3 and 3, 5 and 5, but the 0 here is not over here. It's missing, and so these are not equal sets. They are also not even equivalent sets, okay? Because this one has 4 elements in it, and this one only has 3. So these are not equal and not equivalent. All right. That concludes 2.1. You should go on to 2.2 at this time.